Hi everyone. In this video, we're going to go over the Diels-Alder reaction, which is one of the pericyclic reactions. So your textbook does also cover electrocyclic reactions and sigmatropic rearrangement, but we're just going to cover the Diels-Alder reaction. So don't worry about those other two if you're reading the textbook. All right, so what are pericyclic reactions? Let's start there. So pericyclic reactions are reactions that do not involve either ionic or radical intermediates. So really, in a pericyclic reaction, everything happens in one step, so we don't have any intermediates. All right, now in order for the Diels-Alder reaction to occur, we need a diene, so a molecule with two double bonds that are separated by a single bond. And we need an alkene, also called a dienophile. So dienophile means that this molecule really wants to react with a diene. It really likes dienes. Now notice that the diene is in the S-cis configuration, where the two double bonds are facing in the same direction. Now, the reason that they have to face in the same direction, so they have to be in the cis configuration, is due to the fact that this is less stable than the S-trans configuration, which means that it's very reactive. So the S-trans configuration is much more stable, so it doesn't really want to react with anything. But the S-cis configuration is not very stable, so it's very reactive, which is what we want for this reaction. One other thing about the diene is because it has two double bonds, it's electron rich. So, similar to a nucleophile, it wants to react with something that is electron poor. Now, looking at our dienophile, that is also electron rich, right? So we should probably add something that will make it electron poor so that it reacts more efficiently with the diene. Now, this reaction does still occur even without adding stuff onto the dienophile, but the percent yield is really low. It's about 20%. But in this reaction, all of those pi bonds are going to move around and create new bonds so that we end up with a ring structure. All right, and let's just highlight the new bonds that formed. Oops. I'll just redraw the new bonds there. There we go. And then the pi bond, one of the pi bonds moved over one position to create a double bond. All right, so again, in order for this reaction to occur more efficiently, we need to make the dienophile electron poor. So what we can do is add electron withdrawing groups, so EWG. And I'll just write that up above as well. So EWG stands for electron withdrawing group. So this would be something with really electronegative atoms like oxygen or maybe a bromine, or even like a nitrogen. So just something that's more electronegative than carbon. Okay, so once we add those electron withdrawing groups, notice that I drew them cis to each other. So on our product, they would also be cis to each other. So we'll draw them both as dashed positions. And notice that this molecule that we've produced has a plane of symmetry. So this is a meso compound. Okay, so again, let's just make a note under the dienophile. It is electron poor due to electron withdrawing groups. Now, this reaction was discovered in 1928 by Otto Diels and Kurt Alder. Oops. So let's just make some notes here. Just a little bit of history. That's why it's called the Diels-Alder reaction. I don't know how they decided who got to go first in the name, but... And they actually won the Nobel Prize in Chemistry in 1950 for their work. All right. Now, there are a lot of advantages to this Diels-Alder reaction, so let's just make some notes about that as well. So one of the advantages is that you create a ring structure. Also, this is really easy to perform. So as you all saw in the Diels-Alder lab, really you just mix stuff together, turn on the heat, let it reflex, and you get your product. So it's really easy to create the product. But additionally, you can also control the stereochemistry of your product. So if you need to make a very particular molecule, that can be another advantage. Okay, so let's just go over some examples for the Diels-Alder reaction so that you can get a feel for the types of products that would form. All right, so let's start with the following. Okay, so we have our diene on the left, and it's in the S-cis configuration, which is what we want. And then we have our dienophile, and the electron withdrawing group, oops, is the cyanide group. So a carbon that's triple bonded to a nitrogen. All right, so pause the video and see if you can figure out what the product would look like. And remember to show stereochemistry for the cyanide groups. So would they both be in dashed positions, in wedge positions, or would they alternate? Would one be a wedge or one be a dash? And then when you're done, we'll go over it together. Okay, so let's show the arrows for this mechanism. So remember, the pi bonds are going to move around and create new bonds. And then we're going to move one of our double bonds over one position. So this is actually going to form two rings, because we already had a cyclohexane ring on our diene, and we'll have a double bond right down the middle. And then we have to remember our cyanide groups. So they're both cis, and they'll actually both be in the wedge position. And we'll talk about why later on. All right. Now let's look at one more example. What if we have the following? Okay, so we've got our diene and our dienophile. See if you can figure out what the product might look like. So you can pause the video, and when you're done, we'll go over it together. All right, so this is actually a trick question. Notice that the diene is not in the S-cis configuration. It's actually S-trans. So those two double bonds are opposite from each other. So this reaction would not occur. And I'll just highlight that the double bonds are opposite each other. Now, remember that if we had an open chain system, so let's say we didn't have a ring structure for the diene, S-trans can rotate to form S-cis if we add enough energy. But with this ring structure, the diene is stuck in that S-trans configuration. So let's just make a note that in an open chain system, S-trans can rotate to S-cis given enough energy. But again, because we have that ring structure, we can't easily rotate it into an S-cis configuration. So we wouldn't see a reaction in this case. Okay, let's go over another example. Okay, so let's talk about this one because notice that the diene is in the S-trans configuration. But remember, if we have an open chain system like this one, those bonds can rotate given enough energy. So if we add 15 kilocalories per mole of energy, the S-trans molecule will rotate into S-cis. So remember we went over this rotation in a previous lecture. So the 15 kilocalories per mole has been measured previously, and that's how much energy is needed for S-trans to rotate into S-cis. Okay, now let's look at our dienophile, which has a triple bond instead of a double bond. Okay, so that's new. And remember, those R groups are just alkyl groups, so something with carbons and hydrogens. Okay, so if you have a triple bond, it doesn't really change how the reaction works. So dienophiles can be double or triple bonds. Okay, so we're still going to create some new bonds, and one set of pi electrons from our triple bond will create another new bond, and then one of the double bonds will just move over one position as normal. So this time, we are moving one of our double bonds over, And the triple bond is going to become a double bond. And then we'll have our R groups kind of facing away. So let me just highlight our double bond there. And then the pi electrons, or one set of pi electrons, becomes one of our new bonds. And another set of pi electrons becomes our other new bond. Okay. So again, the overall reaction here is going to give us this ring structure. And just make a note, dienophiles can be double or triple bonds. So this is really cool because if you needed to make a product with two double bonds, like the one we made here, that is possible. You just have to start with a triple bond for your dienophile instead of a double bond. Okay, so let's look at the molecular orbitals for this type of reaction. So remember, in a previous lecture, we talked about how conjugated pi systems can have different molecular orbitals depending on how the p orbitals line up. So, for instance, let's say we're reacting 1,3-butadiene in the cis configuration with just a simple alkene there. So we have p orbitals on each of these carbons here. And then there's p orbitals on our alkene as well. And remember that p orbitals have a blue side and a red side, so the lobes are slightly different. Now we also saw that the HOMO of butadiene, or the highest occupied molecular orbital, that was a situation where the two p orbitals on the left were aligned with each other. So let's just draw the electrons kind of delocalizing there. And then there was a node in the middle where electrons don't exist, or at least the pi electrons don't exist. And then the other two p orbitals were aligned with each other. All right, so that's what's shown down below. We've got our two red orbitals aligned, or two red lobes aligned, and then the two blue lobes are aligned behind that. Okay, now in order for this reaction to occur, the highest occupied molecular orbital for butadiene is going to align itself with the lowest unoccupied molecular orbital of ethylene, which is our simple alkene. So let's draw what that looks like. All right, so the lowest unoccupied molecular orbital for our simple alkene has two p orbitals, but they're not aligned with each other. So there's a node down the middle. But this would be the LUMO of ethylene. So remember, we talked about how the HOMO and the LUMO, that's where all the chemistry occurs. And those were called the frontier orbitals. So what's going to happen here is electrons from the highest occupied molecular orbital of butadiene those are going to get transferred into the lowest unoccupied molecular orbital of ethylene. So again, the LUMO of ethylene doesn't have any electrons, so it can accept them from the HOMO of another molecule. Okay, so that's why we end up with these new bonds. We get a bond between the two blue lobes there, one from butadiene, one from ethylene, and then we also get a new bond between the two red lobes there behind that, if that makes sense. But you can also see that in our final molecule here. We've got alignment between those lobes, and we get our new bonds. Okay, so now we have our final product, and notice that it's in a different configuration than we're used to. So normally we see cyclohexane in a chair conformation, but this is actually a boat configuration or boat conformation. So it kind of looks like a boat that's upside down. All right, now this very specific interaction between the HOMO of butadiene and the LUMO of ethylene, that's going to dictate the stereochemistry for our products. So let's look at an example of that. Okay, so let's go back to the first example I gave you where we had our S-cis diene, and then we had our alkene with cyanide groups attached. So those were our electron withdrawing groups. Now, again, we said that the electron withdrawing groups were cis to each other. And we said that in the product, they would also still be cis to each other. All right, so that again, that has to do with how the two molecules interact with each other. Now, let's look at another example. So let's say instead of the two electron withdrawing groups cis to each other, let's say they're trans to each other. Okay, so what would happen? Well, we would still see new bonds forming, exactly the same as before. So we would still have that cyclohexene ring, but this time the electron withdrawing groups are trans to each other, so we want to make sure that they're trans on the product. So what we'll do is one of the cyanide electron withdrawing groups will be in a dash position, and the other one will be in a wedge position. Now, in this case, we're not forming a meso compound. So remember, in the last example, oh, I forgot to draw my arrows. Let me just draw those arrows real quick so we can keep track of our movement of electrons. But in this example, remember we formed a meso compound. And meso compounds do not have enantiomers because there's a plane of symmetry. But in this situation, we have two stereocenters, and what if we had drawn this the other way? What if the top cyanide was a wedge and the bottom cyanide was a dash? So that would form a non-superimposable mirror image. So in this situation, we have an enantiomer, that forms as well. So we actually get two products. Now, looking at our original alkene there, the cyanide group that's kind of pointing away from the reaction, we're going to say is pointing out. And then the cyanide that's kind of pointing towards the reaction, we're going to say that's pointing in. And that can also have an effect on what our product will look like as well. Okay, so we're going to stop here today. In the next video, we're going to go over some more examples of what our products would look like given, these different electron withdrawing groups and how they're positioned. But also the diene could have groups attached to it as well. So we're going to try to see what our product would look like depending on groups that are attached to either the diene or the dienophile. So I will see you then.